In this class, we are going to look at factors that influences reaction mechanism. Before we talk about the factors, there are some basic things we need to understand, which are what is nonpolar and polar bonding. In a covalent bond, the electron cloud between the atoms are not static, meaning that they are mobile. So when the atoms involved in this covalent bonding are similar, example is hydrogen molecule or chlorine molecule, this electron cloud that is not static is going to be shared equally, which is called symmetrically disposed between the two atoms. This kind of bonding that involve similar atoms are called non-polar covalent bonding. A covalent bonding that involves atoms that are not similar. A typical example is hydrogen and chlorine. Because there are differences in electronegativity between these two atoms, the electron cloud between them are not shared equally, but it tends towards the highly electronegative atom, in this case chlorine, meaning that the electron cloud are not symmetrically disposed. This kind of bonding is called diagram. You can see how hydrogen molecules and chlorine molecules are being symmetrically disposed of the electron cloud between them. While hydrogen and chlorine, the disposition is towards chlorine because it is highly electronegative. Into some of the factors that have to influence reaction mechanism. The first one we're going to look at is inductive effect. This effect is effect whereby a non-polar covalent bond. Remember, we are talking about when a bond is covalent, it is non-polar, that it means that similar atoms are involved and the electron cloud are shared equally. So carbon and carbon are non-polar bonding because they have the same electronegativity. Hence, they are now polarized because carbon and chlorine bond are polar because chlorine is highly electronegative. Like we talked about in the previous slide, that when atoms that bond together have difference in electronegativity, they are going to be called polar bonding. So because carbon and chlorine is polar, the carbon-carbon that is non-polar becomes polar because the neighbor is polar. And that is why we can see in that structure that the farther away of this carbon from carbon chlorine, the lower the polarity. So the closer the non-polar bond to polar bond, the more polarized. Distance affects inductive effect. What's the essence of inductive effect? Remember, characters of inductive effect, they are permanent effects. This is manifested in their properties like dipole moment, and this inductive effect can only occur in a saturated system through sigma bond. Of inductive effect, there are negative and positive inductive effects. In negative inductive effect, we are talking about electron withdrawing substituents. Whenever there is a withdrawal, is a negative effect. And remember, when electrons are being withdrawn, the compound increases. The significance of inductive effect, of negative inductive effect, is increase in acidity. So the more we have this negative effects, negative inductive effect, the more we have this electron withdrawing substituent on a compound, the more the acidity. This is typical example of if we are having a compound that has one chlorine, another compound that has two chlorine. The one that has two chlorine is more acidic by inductive effect than the one that have one chlorine. In the same manner, positive inductive effect. When there is positive inductive effect, electron is being donated. And when electron is being donated, there is increase in electron density. When electron is being withdrawn, that decrease the electron density. Increase in electron density is going to increase polarity, is going to bring about high basicity. While electron withdrawing is going to reduce electron density, making the compound more acidic. So the more we have alkyl in a compound, the lower the acidity and the higher the basic potential of that compound. So this is a significance of inductive effect in reaction mechanism. So from this slide, you can see that the more alkyl is donating to carbon, from the slide we can see the first compound is more basic and less acidic. So from this we can say that the one that have methyl is more acidic, while the one that have 3-methyl is less acidic and more basic. Acidity and basicity are interchangeably. When a compound is more basic, it is less acidic, and vice versa. We're going to look at that affects reaction mechanism is electromeric effect. In electromeric effect, there's a complete transfer of this shared pair of electron. Remember, the carbon and oxygen bonded by multiple bond. In that multiple bond, it involves 2 covalent bonding. Now, the pi bond, which is weak bond, is going to be the electron between carbon and oxygen by pi bond is going to be transferred to oxygen by the presence of a reagent. So why this is a temporary effect is that it does not happen on its own. It happens because there's an attacking reagent that induces the complete transfer. So meaning that in absence of this reagent, this compound is going to reverse back. That's why it's a reversible reaction. And then a temporary. Another character you need to know that it does not occur on a sigma bond or in a saturated system, just like inductive effect. Is that the unsaturated carbon, the pi bond is the one that is moving. Remember, in resonance, only the bond electrons move. The atoms are not mobile. Then this electron cloud between in unsaturated system is going to move. When it moves, the carbon 1 and 2 that was unsaturated is going to become saturated. Remember, unsaturation is talking about increase in electron density. So there is a corresponding decrease in electron density from a compound that had increase, and there's a corresponding increase in electron density in a compound that has decrease. So that's what we talk about in resonance. Now, for a compound to undergo resonance, there must be double bond, alternating single bond in conjugated system. And these bonds depend on one another in electronic interaction, in the sense that when one bond is decreasing, another one is increasing simultaneously. So they cannot work independent. They are always dependent on each other. Now, double bond or triple bond that are separated by more than one single bond are not called conjugated. They are isolated. Isolated compounds behave independently, meaning that each bond can undergo reaction as if the other one does not exist. This kind of compound cannot undergo resonance or mesomeric effect. Resonance is simply the ability of pi electrons in a conjugated system to move in between atoms. It is the pi electron that is moving in resonance, and it results in alternation of electrons between atoms in a molecule, meaning that an atom that has unsaturated at the end may become saturated, while the one that is saturated becomes unsaturated. Remember, this electrons are mobile, and so they move within the bonds, and it is only the pi electron that is moving. Then this, when there is this alternation, we are going to have canonical structures, which are resonance structures. The molecule that has more of these resonance or canonical structures is more stable, and the more stable a compound, the more the acidity. That's why when in a resonance, when a compound has so many resonance structures, that compound is regarded as more stable and more acidic. Canonical structures or resonance structures have higher energy more than the hybrid, because in hybrid there's equal dispersion of this negative charge. What are the tips in writing resonance? First is that curved arrows are always used to show the progress of one resonance symbol to another. In terms of shifting of electrons, use curved arrows. Now, it is also noted that the nuclei in these atoms are not moving. The atoms are not moving. It is only the electrons that move. And pi electrons or unshared valence electrons can also be shifted, not just only on saturation. Unshared electrons can also be delocalized. The electrons moving is just an artificial thing, because electrons don't shift, they are just delocalized. You don't shift electrons, you delocalize electrons. So issue of shifting is purely artificial. There are two types of arrows we use when we are talking about resonance. We can use double-headed arrows, meaning the electrons are being shared or shifted at the same time equally, and we can use a single one, meaning one at a time. In using two-headed arrows, we are going to form radicals. When we are going to use single one, we are going to call for either carbocation or carbanion, depending on the movement of this single arrow. Where the single arrow is moving towards is going to form carbanion. Where it is moving away from is going to form carbonium ion or carbocation. There are types of structure that show resonance. Number one, structure that have double bond or triple bond in conjugation. Remember, conjugation is a multiple bond alternating single bond. When a compound is an isolative system or cumulative, isolated is when double bond is separated by more than one single bond, while cumulative is when single bond is separated by more than two double bonds. Compound that undergo resonance, structure with double or triple bond in conjugation to an atom having p orbital. This p orbital can contain two electrons. It can contain one electron, and it can also be empty. In containing two electrons, we are going to have, as seen on the slide, now this chlorine atom having lone pair of electron is going to move. Now, when this electron is moved, remember in resonance, they are always working independently. So as this is the lone pair of electron is moving to form double bond, the double bond already existing is going to break out. That's why we got structure 2. The structure 3 is a hybrid structure where those negative charges have been dispersed among the atoms involved in the resonance. In p orbital that had just one electron, this one electron on it is a radical, and that is why for you to form bonding unsaturated or double bond using radical, you're going to have also create radical. When two radicals come together, they're going to form a bond. So the radical on methylene carbon is going to be delocalized. Then the unsaturated compound already is going to be shared into two to generate radical. So at the end, we are going to form another radical in the left end of the carbon, while we started the radical at the right end of the carbon. So at the end, there is decrease in electron density from unsaturated system to the carbon that had radical, and the carbon that was unsaturated there is increase in electron density from carbon that had unsaturation to carbon that had radical, whereas there is decrease in electron density from carbon that have unsaturated. So the one that have unsaturated now have decrease in electron density by having radical, while the one that have radical have increase in electron density by having unsaturation. The next one is when the p orbital is empty. In that case, we are talking about allyl carbocation. Remember, when we are having carbocation, we need cation for us to form a double bond. In that same manner, what happens in B above when we have radical is the same thing that will happen. But the difference here is that we are going to use a single arrow to create a cation on the middle carbon, forming unsaturation on the terminal carbon, just like the structure number 2. The next compound that undergoes resonance is hyperconjugation. The first one is a compound that have a single bond or multiple bond in conjugation. Second one is when the compound have p orbital. The next one is hyperconjugation. Hyperconjugation is a kind of a structure that involves sigma bond electron as well as pi bond. Now, it depends on there must be a presence of at least one hydrogen atom that is alpha to unsaturated system. This unsaturated system can be sp2 hybridized, it can be a free radical, and it can also be a carbocation, just like we saw in the previous slide. With free hydrogen alpha to sp2 hybridized. Remember, in this case, we are talking about in resonance, in hyperconjugation, is a movement of bond, just like normal resonance, without the nuclei or the atom moving. So that's why it's called no bond resonance. This is a kind of resonance where the sigma bond that is not supposed to move is going to move without affecting the nuclei or the atom. From this slide, you can see that hydrogen still maintains its own position, while the bond between hydrogen and carbon does not exist. That's why hyperconjugation is called no bond resonance. And in this hyperconjugation, the more the hydrogen on alpha carbon, the more the resonance or canonical structures we are going to get. What happened in sp2 hybridized? In sp2 hybridized, the bond is one that is moving. The bond between carbon, alpha carbon, is going to move, and the one in unsaturated system is going to break and deposit on the terminal carbon. Remember, in resonance, they work dependent on each other. So when there is electronic transfer from one end, there must be a simultaneous transfer on another end. So there is increase in electron density at alpha carbon and decrease in electron density in unsaturated carbon. With free hydrogen alpha to free radical. Whenever you talk about free radical, you realize you need radical to form bonding for radical. The first one of sp2 hybridized is movement of bond. This second one, we're talking about radical. So that's why we're going to use two half arrows to create radical. At the end, the hydrogen there is going to be no bond resonance, is going to be a hydrogen radical. Then this hydrogen is going to break into to form another radical. And the radical on the terminal carbon is going to also shift to form an unsaturated system. Hence, we are having non-bond resonance using a free radical carbon. Lastly is a carbocation. Just like we see in that p orbital, the same thing is happening here. But in that case, when we are having carbocation, we need a carbanion to form an unsaturated system. And that's why if you look at the sharing is not like the one of sp2 hybridized, where all the bond is moving. It's part of this one that is very moving. When it's moving, since it's moving towards the bond, it means that it's depositing negative charge, and there's already existing positive charge, both coming together to form a bond, giving us unsaturated system and creating a cation. So these are examples undergo hyperconjugation. What are the rules that governs resonance? First, the relative position of nuclei, that is atoms, must be maintained in all the structures. It's only electrons that are being delocalized from one atom to adjacent bond. And all the atoms taking part in this resonance must lie in the same plane. This will allow for maximum overlapping of p orbitals. This is all canonical forms must have the same number of unpaired electrons, meaning that looking at the structure, all the canonical forms have the same number of electrons, except IV. Now, because of other canonical structure have positive carbocation and carbanions, but IV have radicals. So that's why IV is not a canonical form, because it has two lumps of electrons, while others have carbocation and carbanions. So that is how to identify canonical forms, because they must have the same number of unpaired electrons. Then the energy of the resonance hybrid must be less than each of the canonical forms. So the resonance hybrid is more stable. Just like all canonical forms must not contribute equally to the hybrid, meaning that the canonical contribution depends on the stability of the structure. The more stable a canonical form is, the larger its contribution to the hybrid. You contribute according to your capacity. So that's what happens in canonical contribution. And the more canonical forms, the greater the resonance stabilization. And the more the resonance, the more the more acidic the compound becomes. How do I know a compound that is more stable or have more stable canonical forms? First, they must have higher covalent bonding. Secondly, they must have decrease in charge separation. Looking at structure 1 and 2, which of them is more stable of a canonical form? If you look at 1 has 5 covalent bonding, while 2 have 4. There is no charge separation in 1 and there is charge separation in 2, making 1 more stable than 2. A canonical forms must obey octet rule or duplet rule. That is, period 2 must have a maximum of 8 electrons, obeying octet rule. Hydrogen must obey duplet rule. Looking at the structures, you realize that the third structure has 10 electrons for chlorine, making it not to obey the octet rule. That is why it is not a stable canonical form. How do we know a canonical forms? A canonical forms that bears negative charges on more electronegative atoms are more stable than the one that bear negative on less electronegative atom. Carbon is less electronegative than oxygen. So when I say canonical forms like A that has negative on carbon instead of on oxygen, it is not stable. But when I say a canonical form like B that have negative charge on electronegative atom like oxygen, it is stable. So B. What are the types of resonance effects? We have positive and negative resonance effects. When there is a presence of electron donating substituents on a compound, we talk about positive resonance effect. These electron donating substituents are going to increase the electron density in that compound. Example is amine and hydroxy group. But when an electron withdrawing substituent is attached to a compound, we are going to experience less electron density called negative resonance or negative mesomeric. Resonance can also be called mesomeric effect. Is supposed to be known. Example is carbonyl and NO2. What are the essence of this resonance effect? It helps us to explain the relative stability of reactive intermediates. Because when a compound has so many resonance, you can confidently say this compound is more stable because the charges are being dispersed around all the compound, just like in terms of aromatic compound. You realize that all the negative charges is going to be dispersed around the corners, all the sides of this benzene ring, making it more stable. So the more the resonance. Now, the next thing we need to talk about is how do we generate this reactive intermediate compound. It can be generated in different ways, either homolytically, when the bonds involved are being shared equally, forming radicals. We call it homolytic fission. Fission is breaking. Then when this bond is being cleaved heterolytically, we are going to form carbocation or carbanion, depending on the movement of this arrow. Remember, in homolytic cleavage, you are going to use half arrows, while in heterolytic cleavage, you are going to use full arrows. In that full arrows, when the bond is moving towards an atom, that atom becomes a carbanion. When a bond is moving away from the atom becomes carbocation. So in heterolytic, we are going to form carbocation and carbanion. Remember, it involves unequal cleavage, while homolytically involve equal cleavage. Free radical is just an atom or group of atoms that possess odd or unpaired electrons. These free radicals are being obtained using homolytic cleavage. And the order of stability of this free radical is as shown. Benzyl free radical and allyl free radical are very stable and are more stable than tertiary, and the least is methyl, meaning the more these substituents electron donating capacity of our K group, the more stable radical becomes. In carbocation, we're talking about a compound, a group of atoms that contain carbon that have only 6 electrons. That's why it's being represented by positive charge. This typical example are seen in our K group, methyl, ethyl, and such likes. The relative stability of this carbocation is just like that as seen in radical. Benzyl carbocation and allyl carbocation are very stable, and tertiary is more stable than methyl because the more the electron donating, the more stable the positive species, because this is positive. So when positive is like deficient, when you give to a deficient person, the person is stable. So that is why electron donating stabilizes carbocation. This carbocation, like said in previous slides, you can do that by heterolytic fission. You can also do that by addition of a proton or any positive species to unsaturated system. Anion is also a species with negatively charged carbon atom. Is also represented by negative charge on carbon. Anions are the strongest bases, classes of bases, because of their lone pair of electrons. Now, unlike radical and carbocation, the relative stability of carbanions differs when you come to alkyl. Benzyl and allyl are very stable, but methyl carbanion is more stable than tertiary carbanion because the more this is negative, it has high electron density already. So releasing to one that has is you're going to make it to be more stable. more unstable. Just like somebody that is saturated already with water, I want to give that person water, the person will end up vomiting because the person is is already stable. So you want to make that person uncomfortable. But when somebody is very dry, has dry throat, that is deficient of water, the more you give the person water, the more stable the person becomes. So that is different between radical, carbocation, and carbanion instability. In radical and carbocation, they are deficient. When you donate electrons to them, you make them stable. While in carbanions, they have excess electron density. Releasing more electron into the one that is already have excess electron density is going to make that compound be less stable. So that is why tertiary is less stable, while methyl is more stable. Anions, just like we did in cations by heterolytic fission and by addition of negative species to unsaturated. From what we've done so far, what is the most stable of the species? It is evident that the most stable of the species is carbanion because it has higher electron density, so it is more stable. Cyclic and allylic species, the canonical structures. Remember we said the more the canonical structures, the more stable a compound is. So these allylic structures are very stable because they are resonance compounds. They are stable by resonance. The localization of these electrons, radicals, carbocations, and carbanions is going to make this compound to be very stable. Happen in benzylic species. Why are they stable? Because they are stabilized by resonance. The more the electrons being able to be delocalized within the aromatic rings, the more stable the compound is. So whether carbocation, whether carbanion, whether radicals, they are very stable because they are being delocalized. They can be stabilized by resonance. Effect. Talk about steric effects. Talk about ability of electrons or a reaction to be influenced negatively by presence of bulky groups. So when the higher the number of bulky group in a compound can make the compound not to react or to react slowly. So this effect is called hindrance, steric hindrance. Example is that a car carrying so much load and a car that is not carrying load, their speed differs. The more the load, the lower the speed of this car. This load is called steric effect or steric hindrance. Compound structure 2 has so much steric that the reaction, there's no space for any reaction to occur here, unlike the compound is unlike the structure in 1, because there is still space, the reaction can still occur, while no reaction can occur in 2 because of steric effect. Questions again. Identify and circle the most stable carbonium ion. Remember, carbonium ion is same thing as carbocation. Now, the second is more stable because the benzylic species. There's direct contact with carbocation and the bonding in aromatic system. The second one, the more the methyl, the more stable. So that's why propyl carbocation is more stable than ethyl carbocation. The third one, tertiary, is more stable than methyl. So the third one is tertiary. I hope you understand. Identify the ion that will be more resonance stabilized. The same thing that we talk about in benzylic species make the first structure in I to be more resonance stabilized because there is direct interaction with this carbocation to aromatic system. The second one in II, the second structure is more stable because of stability by resonance using carbocation and unsaturated system. In the third III, the second structure is more stable because electron withdrawing effect of NO2 is going to make the high density of methylene, negative charge of methylene, to be stable, while electron donating capacity of methyl is going to make this CH2 to be more unstable, because you're increasing the electron density in a compound that has high electron density already. I hope that's clear. So go through this, make sure you understand it, and if there's any question, don't forget to drop in the comment section and you'll be responded to. Chemistry is not difficult. Don't live life alone. Always interact with your classmates, and you are free to also interact with me on the comment section. See you in the next class.